12. The laws are quite complex, and you're going to have to forgive me that they are somewhat complex, even beyond myself, even beyond my own knowledge. So David, John, Kent, Jeff, and Leanne, I hope you'll be okay. I'm going to introduce today's chapter. I'm not sure if you've watched any of these yet, but it's 3D videos to explain some context, and then we'll go into the chapter itself.
Hilchos Kiddush HaChodesh, chapters 12 and 13. In the beginning of chapter 12, the Rambam states that in 24 hours, the sun proceeds in the Galgal HaMazolos a distance of 59 minutes and 8 seconds, almost an entire degree each day, as explained in the previous lesson. Together with its daily westward revolution around the Earth, the sun also moves eastward, propelled by its own sphere, based on the daily figure stated above of 59 minutes and 8 seconds. One can calculate the angular distance traveled by the sun in 100 days, a year, or many years. In Halacha Beis, the Rambam gives the sun's exact position on the third day of Nisan in the year 4938 after creation. Having established this starting point, one can determine the Emtza HaShemesh, the sun's mean location, on any given date, simply by taking the figure mentioned above, 59 minutes and 8 seconds, and multiplying it by the number of days that have passed since the date of the starting point. This will give the location of Emtza HaShemesh at 6 p.m. on any given date. Nevertheless, further calculations are necessary to determine the exact location of the sun. Emtza HaShemesh is the sun's location on the path of its orbit. Notice, the Earth is not in the center of the sun's orbit. The point where the sun is furthest from the Earth is called the Gova, apogee. When the sun proceeds a certain angular distance on its orbit, it will not be seen at that same angular distance from the Earth. Our model is exaggerated in order to make the concept clear. For example, this bit, it will be seen at 25 degrees from the Earth, a difference of 5 degrees. This is the Mokum Amiti, the true position of the sun, as seen from Earth. At 60 degrees in its orbit, its Mokum Amiti will be 50 degrees, the difference of 10 degrees. At 90 degrees, its Mokum Amiti will be 78 degrees. This is the greatest extent of the difference. From 90 to 180, the difference will begin to decrease. At 180 degrees, there will be no difference. After 180 degrees, instead of subtracting from the angular distance, we will begin adding to it. In chapter 13, the Rambam gives a table to compensate for the variation between the sun's position in its path and its true position as seen on Earth. These are the Munois Hamaslul in Halacha Dalid. One further factor must be considered in order to determine the true position of the sun. The path of the sun and the Gova also move. That movement is very slight, as the Rambam states in chapter 12, Halacha Beis, it is 1 degree in 70 years. Nevertheless, this causes the variations calculated above to take place at different angular positions. So, to find the true position of the sun, we must calculate where the sun is in its orbit, and also where the Gova is. Having determined the distance between them, we can now implement the Monois HaMaslul to find the Mokum HaAmiti, the true exact position of the sun as seen from Earth.
Okay, so I hope that gives you a little bit of insight. What we're going to do now is the shir and the actual text is going to be from Rabbi Mendy Lipsker from Sherman Oaks, California, a very dear friend of mine. and quite a bit of an advanced scholar. He understands these halachas much better than I do. What I would suggest is perhaps minimizing the screen of the Zoom, and let me put it into the text here as well, into the chat box, in case you didn't get it on the WhatsApp group. So that link that I just posted there, that's the Rambam for today. So you can click on that, and then we'll go to Rabbi Lipsker.
Previous chapter about planet movement and the placement. Chapter 12. We are continuing now to study about the calculations and mathematics that the Beis Din used to use to figure out if the moon would be sighted on the night of Rosh Chodesh in Jerusalem. So after laying the ground rules in the previous chapter about planet movement and the placement of the latitude and longitude of Jerusalem, where references are made to, we continue now to learn in this chapter about the movement of the sun and the establishment of the position of the sun in its orbit. Halacha Aleph. There are two long halachas in this chapter. The average movement or travel of the sun in one day. We learned in the previous chapters the sun has an annual movement of either 365 and a quarter, according to one opinion rounded off, or a little bit less than that. In actuality, even a little bit less than the second opinion. Now he goes into exact movements by day, by week, etc. So how much does the sun travel in a 365-degree orbit every single day? We're talking about the sun's annual cycle, which is from west to east. The fact that we see sunrise from east to west, that is not the sun's orbit. That is either, depending on which opinion in the sages you follow, either the earth turning on its axis, which makes a sunrise and a sunset, or, as Rambam puts it, the entire universe spinning around the earth. But here we're talking about the sun's orbit under the sky, underneath the constellations of the stars, moves from west to east. 0 degrees is the constellation of Aries, and then going westward, then going from east to west, moving away from 0 to 90, from west to east. Okay, not the way we see it, sunrise, sunset, but it's actually, let's put it kind of counterclockwise, if we make a circle on a paper. 0 degrees, then that's the Aries, 30 degrees, and then from 30 to 60 we learned is the bull, and then from 60 to 90, the twins, etc., etc. So the sun's movement in one day, we established the day is 24 hours, 59 minutes and 8 seconds. These are spatial curvature spaces, as we learned. The circle has 365 degrees. Every degree is divided by 60 sections, which we call minutes. Every of those sections are divided again by 60, which we call seconds here. So it goes slightly less than 1 degree. 1 degree is 60 sections, 60 minutes, and here it's 59 minutes and 8 60ths, which is 8 seconds. Simanam kad natach. That's how much it travels in one day. Slightly less than 1 degree, which will equalize how in 365 days the sun only travels 360 degrees. The sun travels 360 degrees a full circle in a year. A year has 365 days, so obviously it's going a little bit less than 1 degree every day, so it concludes its circle in slightly over 365. Nimsam halacha basara yamim. Now the Rambam is making calculations easy for us. So in 10 days, you multiply 10 times what he just said before, is Teisha Mailas Vechad V'Chamishim Chalakim V'Shalosh V'Esrim Shniyos. So in 10 days, Simanam Tana Chag. It's 9 degrees, 51 minutes, and 23 seconds. Now in actuality, if you did the math very fast right now, you notice that it's a little bit over times 10, which we just said of 1. Because the sun's movement in one day is really slightly more. It's 59 minutes, 8 seconds, and we learned in last chapter there's another subdivision of thirds, and it's really 19.8 thirds. But this is such a tiny fraction that when it comes to one day, the Rambam leaves it out. But when it comes to 10 days, since it's already another second, he adds it together. So he, like he said in the beginning, don't pay attention if you think I missed some things because I make it up in a later time. So how much does the sun travel in its orbit? 100 days. In 100 days it travels 98 degrees, 33 minutes, and 53 seconds. Simanam tzach lagnag. That's the acronym. I guess for people to be able to remember this quicker, he gives these short acronyms. So how much does the sun travel in 1,000 days? 1,000 days is almost 3 years. Well, 1,000 days is much more than 360 degrees. So how do we do that? So we learned the remainder that the sun travels, because after the course of 1,000 days, when you take all the 360 multiples, you subtract them, because every 360 you start again from 0. It's back to 0. So in 1,000 days, it makes a few circles, and how much is left? Where is it in the orbit from 0? It traveled 265 degrees, 38 minutes and 50 seconds. How much is the remainder in 10,000 days? That's like 25 or 28 years. So, but when it keeps on going around and around, where is it now in the circle? Which is 136 degrees, 28 minutes and 20 seconds. In the symbols, again, 136, 28, 20. So the Rambam is doing the calculation for us, just saying, here is major points: 1 day, 10 days, 100 days, 1,000 days, 10,000 days. Now that you have this, he says, now that you know how the formula works, you can do your own math and find how long it travels in any amount of days that you want. If you want to make, like I made, pre-calculated figures, the Rambam just did 100 days, 10 days, 1,000 days, 10,000 days, so you can make your own groups. For its traveling of 2 days, 3, 4, Adasara till 10, Tasa. You can do that. You can do a 5-day pre-calculated. Also, if you want to have pre-calculated figures for 20 days, 30 days, 40 days until 100, of course you can do it. This is very evident mathematics. Figure, you know the exact for 1 day. And like we said, it's a tiny fraction off, but he makes it up in 10 days and 100 days. So you just multiply, you just do the rest of the numbers and you figure it out. So which pre-calculated should we have? He says, it would be proper to know another 2 amounts. Now we know 100 days, 1,000 days, 10 days. He says, let's do a pre-calculation for something which is more relevant to us, what we're studying right now. What should we know? You should know you should have the amount that the sun travels in 2 important numbers. One is 29 days and 354 days. Why 29 days? We're going to say in a minute. Why 354? Right now he says it. How long is the lunar year? Our calendar, 5772. If the months are in order, which we learned already, Cheshvan and Kislev, the 2 months after Tishrei, can either have 29 or 30 days. If it's 29 and 30, that's called in order, the regular year, the regular pattern, and that's 354 days is the year. So the lunar year in our calendar, the regular year is 354. You want to know how much the sun travels in that amount of time. When you will have these numbers, how much the sun travel in 29 days, how much does the sun travel in 354 days, this will facilitate, this will make it easy for you to understand the possibility of the new moon. And he explains why. So once you know how much the sun travel in its orbit in 29 days, or 354, it's an easy number to make reference to figure out the new moon. And he explains it simple. Because there is only 29 complete days from one sighting of the moon to the other sighting of the moon. It's never less and it's never more. It's impossible to have between one sighting of a moon and another sighting of a moon less than 29 days, and it's impossible to have from one sighting of the moon to the next new moon more than 30 days. It's 29 and something. Always. Why? Very simple. The moon travels in its full orbit, we said already, 29 days, 12 hours, and 793 parts. So if you saw the new moon, wherever it was, for the next month to come back to the same position, it cannot be less than 29 days. It can never be more than 30 days, because after 30 days, for sure you saw the new moon already. The same thing in one annual unit. If you saw the moon tonight, when will the moon be seen the next year? The same night? In other words, 1 year later, 12 months later. It can either be 354 days, it can either be 355 days. Some commentaries say it could be 353, and they question why the Rambam omits that detail. So again, the sighting of the new moon works as follows. We always see the new moon right after sunset. On the west side of the horizon, western horizon, there's a conjunction. The sun and the moon meet up with each other. We'll explain that more in later chapters, but it was explained already in the previous chapters. The sun travels very slowly, the moon travels very much faster. It makes a full circle in 1 month. The sun and the moon meet up together. You cannot see the moon anymore, because the sun is only illuminating the back side of the moon that doesn't face us. And as the moon moves away from the sun, from west to east, it digresses, it runs faster. Then you can begin to see it, the little crescent of the moon. Once the sun set, you have about an hour or less to be able to see the moon, sometimes only a few minutes. So for that position to happen again, takes about 29 and a half days. So it could never happen in less than 29 nights. And after 30 nights, it's impossible not to see the moon. The moon is so far away from the sun, it doesn't only have a thin crescent, it looks like a pretty nice sized banana already. So the only figure that we need to know for our calculations, will we see the moon 29 nights later, or will we not see the moon 29 nights later? So we need to know how much does the sun travel to figure out its position, to figure out the angle versus the moon, and then we'll be able to have these calculations. So it's very practical to have an annual travel of the sun, the moon's lunar year, how much does the sun travel in the lunar year, and how much does the sun travel in the lunar month. So now he gives it, since it's important, here it is, he says. This is once again the Rambam making a statement, what he just said, that all our astronomical calculations here are only relevant to the 29th night after the moon, which means a lot of these calculations are only correct and accurate when the new moon is supposed to be seen. On the 13th of the month, he doesn't address all the calculations and differences of the moon travels and the sun travels because it's not important to us. We are not learning a full astronomical book here. It's only about one night of the month, of every month. Will the moon be seen then or not? How much does the sun travel? The average movement of the sun in its own orbit, which we learned yesterday, is equal every day. So 29 days, it goes like this. 28 degrees, 35 minutes, and 1 second. Again, minutes is a 60th of a degree, and a second is a 60th of a minute in spatial curvature that the sun travels around the circle. How much does the sun travel in a regular year, which is 354 days? It goes like this. 348 degrees, 55 minutes, 15 seconds. So now you know how much it travels in 29 days, how much it travels in 354 days. So this is the first rule to remember, that when we're going to start to figure out the connection between the sun and the moon, the first thing we need to know is place the sun in the right degree of its orbit. Where is the sun today? In its full circle. So we have to figure out how much it travels every day. Now we still don't know where it is yet. We need to have a starting point. We're going to get there. Another very important rule to how to figure out where the sun is, this is the second halacha. We mentioned it briefly in a previous chapter. Halacha beis, nakuda achas yesh b'galgal hashemesh. There is a point in the orbit of the sun around the earth, and so it applies to all 7 stars, or some say planets. When the star will be in this point of the orbit, it will be, or some say it will be the furthest removed from the earth. We mentioned in chapter 11, halacha 13, the earth is not in the center of the orbit, not of the moon. It's off center, and it's off center from Saturn, it's off center from everything, including the sun. It's not in the center. So when you can see the diagram of the circle of the moon, of the sun. We're talking here about the sun only, sorry. That the inner circle is off center of the outer circle. The outer circle is the order of the constellations. Those are the stars. The earth is the center of that circle, and the sun is moved off center. So there is a point in the circle of the sun, which is the furthest away from the earth. That point, the highest point where the sun is, because it's off center, so there's obviously times when it's further than the earth. There are times when the sun is a little bit closer than the earth. And 93 million miles, that little bit doesn't make much of a difference when it comes to heat and cold. But for astronomical calculations, it makes a difference in the angle. So there's a point where the sun is removed furthest from the earth, and that point of the sun's orbit and all the other orbits besides the moon, which is a little bit different, which we'll learn in the next 2 chapters from now. That point also moves. It's not the same. In other words, if you have one big circle and another circle, see the diagram, off center, then you would know where's the closest to the earth, where's the furthest. The problem is that entire circle, the high point and the low point also shift from the stars. It's not a stationary orbit as much as the stars are. So it's not, you can say, okay, in the beginning of creation, or whenever it was, the sun's point where it could be furthest from the earth was 40 degrees. And that remains that way. No, the off-centerness shifts also. It travels also on the same line of the degrees, from 0 to 360, from west to east. It goes very slowly. Every 70 years, it travels about 1 degree, approximately 1 degree. This point, this is called the height of the sun, and in Greek, apogeum. Am I saying it right? Apogee, or apogeum in the Greek. By the way, the opposite of the high point is the low point, or the place where the sun is closest to the earth, and that is called perigee, perigeum, or perigee, depending on how you pronounce it. Okay, so once we have this point, there's a high point of the sun in the circle, which is furthest away from the earth. So this is going to be important to us, because when we look up at the sun and we want to place it in the orbit, in our angle, which we are centered under the stars, which we have to know which degree in the constellations it is found. Do we see it? So because the circle is off center, the angle will be different. So this is important to know, where is the sun's high point right now? So this high point, this off center circle, which is the earth is not in its center, it's always off center, but the high point also moves in a sequence very slowly. So here it goes as follows. It's very small fractions. Every 10 days, this apogee travels 1.5 seconds, which means 1 second and 30 thirds. Which is 30 thirds. So in 100 years, it travels 15 seconds. In 1,000 days, in 1,000 days, it travels 2 minutes and 30 seconds. In 10,000 days, it travels not even half of a degree. 25 minutes. 25/60th of 1 degree in 10,000 days. So, 29 days, it travels 4 seconds and a little bit more. How much does it travel in 354 days? In a regular year, 53 seconds. Okay, so we know this concept. When you, by the way, when the Rambam wrote this, until now, it's about 800 and something years ago. So how much did it move in 800 years? Approximately 12 degrees. So the Rambam's position is not accurate to today's position, but we'll see that in a minute. So let's read. We already said in the previous chapter, where do we place our origin? We know that the sun travels this amount in 1 day, this amount in 1 year, but where's the beginning? We have to establish a starting point. So the Rambam put it in his own time when he was writing these laws. It was the beginning of Thursday, which is Wednesday, 6 p.m., which was the third of the month of Nisan, from the year 4,938 years from creation. Where was the sun in its own orbit? The sun itself. Where was it placed? At that moment, which is, we said, all daily placements of sun or moon, etc., in the Rambam's calculations are all approximately at sunset, was Sheva Milos, 7 degrees, 3 minutes, 32 seconds, from the constellation of Aries, which is the sheep. Simanam Zaglab, because this is spring. Spring is always sheep. That's the beginning. So it was 7 degrees, 3 minutes and 32 seconds. Where was the apogee of the sun, the height of the sun? Where was it at that time? Was it that day? Which means again sunset. The height of that day was 26 degrees, 45 minutes, 8 seconds in the constellation of Twins. So how many? That Twins is the third constellation. 30 occupies sheep. The next 30 is bull, and the next 30 is twins. So when we say 26 of twins, it actually means 86 from 0, 45 minutes and 8 seconds. Simonam kav macha. So now you have a starting point. From that, you can move and say and go to any position you want, any date you want, and figure out where it was. So now we're going to begin where this chapter was intended for, to tell us how to figure out the corrected position of the sun, or what we call here in Rambam the true position of the sun. True position of the sun means we don't look at the sun isolated in its own orbit. We look from Earth to the sun, all the way to the stars, and say, when we say our circle around the Earth is the stars, the 360 degrees, we want to look through the sun and say, okay, where's the sun's placement from our perspective to the circle, to the 360 degree heaven around us? That's called the true space, the true place. So here it goes. When you want to know. I correct myself. To figure out the true placement of the sun, the corrected is the next chapter. First, we're going to talk about the average placement of the sun. And the next chapter, the true placement of the sun. When you want to know the place of the sun according to its average movement every day, or any day you want, count how many days passed from this beginning point of the Rambam's day until the day you want. And according to the calculations which we already mentioned, see how distant the sun traveled, how much it traveled. And add everything to the original placement with the kabitz kol minai, and then add up together the summations, the smaller sums, add the seconds, turn the seconds into minutes and the minutes into degrees, and 360 degrees you subtract, goes back to 0. The total is the place of the sun in its average movement for that day. And now he gives an example. We want to figure out and know the average place of the sun. In Friday night, the beginning of Shabbos, the 14th of Tammuz, of that year, which is the starting point for that year. Which year was that? We said already 4,938 years from creation. We count how many days is it from the beginning point until this day that we want to figure out. So we see it's 100 days. So now we know the beginning point, and we want to figure out where is the sun 100 days later. So we take how much did the sun travel in 100 days. We already mentioned before how much it travels in 100 days. 98 degrees, 33 minutes, and 53 seconds. And we add it to the starting point, which was Zaglab, which was 7 degrees, 3 minutes, and 32 seconds. So now what's the total? Where is it? So the total which we will have now is 105 degrees, 37 minutes, 25 seconds. 105, 37, and 25. So add that to the beginning. So where is 105 degrees, 37 minutes, 25 seconds? Where is that? The Mazel Sarton. That is in the constellation of the crab. 15 degrees into the crab. Every constellation is 30 degrees. 15 into the crab. So it's in the fourth constellation. 15 degrees into that constellation. 73 minutes of the 16th degree. When is the sun in that exact place? We already mentioned this, and he goes more exact. It's really 6 p.m. That's what we said. The Rambam's placement of any planet on any given day is 6 p.m. However, for practical purposes, if sunset is 6 p.m., then exactly that's where it would be. It will be on the beginning of the night. Sometimes it will be an hour before sunset. Sometimes it will be an hour after sunset. Why? Depending on summer or winter. Because in Jerusalem, no daylight savings time in these calculations. In Jerusalem, the sunset in the winter moves 1 hour earlier. Sunset in the summer moves 1 hour later. And that's where the placement is. So here we're talking about 6 p.m. and that's it. However, for sighting of the moon, we need to see the moon right after sunset. So how do we deal with this problem of the difference of the hours? So the Rambam says, this detail, do not deal with it. This lack of precise calculations, it has no consequence with regards to calculating the visibility of the moon. We're going to make up for this approximation, this hour of difference. Don't worry, I will make it up in the next chapters, later chapters, when I will figure out the placement of the moon in its own orbit. And the Rambam will add this deal with this discrepancy of winter and summer, a 1 hour difference in the end of chapter 14. This is the way you can figure out the placement of the sun in any given date you want. Even 1,000 years from now. You can calculate all the remainders. We even did 10,000 days, but you can go to 1,000 years if you want. And add the movement of the sun over the beginning time. You will have the position of the sun in its own orbit. Once we deal with the moon or any other planet, we can do the same thing. Figure out how fast it moves. Figure out the placement where it was in the beginning of the year of Nisan, where the Rambam placed it, and then add the additions, and you get the place where you want it to be. Because you know how much it travels in 1 day, and you know the beginning point where you begin from. Add up all the travels throughout the days and years that you want, and add it to the starting point. So you will know the place in its average distance, in its average travel. Says the Rambam, you don't have to stick to my date. I made a convenient starting point because the time that the Rambam lived in. But you can do your own. If you want to make a different starting point, to make your calculations different or easier, different than this starting point that we made in this year, the year that the Rambam was writing it, maybe you want to have a starting point that begins a 19-year cycle. It will be easy for you. Or you want it to be in the beginning of a... Oops, I think I skipped a little paragraph. Let's go back, 3 paragraphs back. The same principle applies to the apogee of the sun, to the high point. You add its travel in those days or the years on the starting point, which we already mentioned where it was. You can figure out where is the high point of the sun's orbit, the apogee of the sun possibility for that day. The same applies if you want to desire a different day, make a different starting point than we chose. So you want to have a starting point that begins by a 19-year cycle, or you want it to begin, you want to have a placement of the beginning of a century. You have permission to do so. What if you want to go back in time? You want to go back 3,000 years. So you can make a starting point backwards. Or many years after my year. The path is well known. Basically, you can either add all the numbers to the sun's movement and establish a later starting point, or you can subtract the movements and go retroactive, and you'll get to an earlier starting point. How do you figure this out? You know how much the sun travels in an average year, which is 354 days. You know how much the sun travels in 29 days. You know how much the sun travels in its orbit for 1 day. And then you know, if we're talking about a Jewish calendar year, that's a complete month, which means Cheshvan and Kislev both have 30 days. It's 1 day more than the average year. The year that has 29 days of Cheshvan and Kislev, there's 1 day less. The Jewish calendar year, the regular year, can either be 353, 354, or 355 days. Then you have the leap year, it can be 383, 384, and 385. If it will be a regular average year, instead of 354, it'll be 384. It'll have an extra 30 days above the regular year. If months are full, which means Cheshvan and Kislev both have 30 days, then it's 31 days more than the regular year, so it'll be 385 days. If the months are missing in the leap year, which means Cheshvan and Kislev are 29 days, then it is shorter than the regular year, 29 days. I'm sorry, it is longer only with 29 days. So it'll be 383 days in that year. Okay, so now you can figure out the movement of the sun in any given year. Because these are all known, established facts, you can figure out the average movements of the sun for any amount of days and years that you want, and add it to our starting point. You can figure out the sun's placement as a new starting point for any date, future date you want. And then begin a new starting point. The other way, conversely, if you want to go earlier than my generation, says the Rambam, you want to go backwards, you can minus the placement of the sun in its orbit from the position that we made in our starting point, and you can have a starting point, an earlier date than the year that we have. And then you can use that date as an average starting point. The same thing you can do with any planet, the same as the moon, in its own orbit. If you know its placement at a certain date, and how long it travels in a day and in a year and in a month, you can go forward or backwards and establish a different starting point that's comfortable for you. And we also, the same principle applies it's apparent, with from what we just said, just so you can figure out the future. The placement of the sun, where it is in its orbit for any future date. You can also figure out where the sun was 2,000 years ago, 3,000 years ago, 4,000 years ago. You just do the math in a backwards order. Thank you for watching. Come again for the next chapter.
So I hope you got some of that.
Yeah.
It's a bit overwhelming. The laws of Kiddush HaChedesh are in a category of their own. But definitely for the numbers guys here, that was definitely good learn.
Yeah.
So, I hope you got something out of it. Have a beautiful Shabbos, everyone.
Thank you, Rabbi.
Thanks, Rabbi.
Thanks, Rabbi.
Shabbat
Thank you,
shalom.
Rabbi.
Everybody.
Good Shabbos, everybody.
Shabbos.
Shabbos, Rabbi. Bye.
Thank you.
Rabbi.
Yes,
Thank you, Rabbi.
I'm just finishing a shiur.